China just dropped $1 billion on glass, and it might be the smartest move of the entire chip war, the wall nobody warned you about. Let us tell you something. The chip industry doesn't love advertising. Every device you own right now, your phone, your laptop, the servers running every AI tool you've used this week, runs on chips. Every one of those chips sits on a base layer called a substrate. It's the platform that holds everything together, routes the electrical signals, and manages heat. Without it, the chip is just a pile of silicon going nowhere. For about 50 years, that substrate has been made from a plastic-like material. Organic resins, fiberglass weaves, that kind of thing. Engineers call it ABF, which stands for Ajinomoto Buildup Film. Yes, it's named after a Japanese food company. The thing holding your AI chip together shares a name with a seasoning manufacturer. That's real. For most of computing history, it worked fine. Chips were small enough, cool enough, and simple enough that plastic got the job done. Here's where it gets interesting. The AI boom changed the rules completely. Modern AI chips aren't single pieces of silicon anymore. They're clusters of multiple chips called chiplets, all mounted together on one shared substrate, designed to act like one giant processor. Nvidia's latest AI accelerators work this way. So do the chips powering the data centers behind ChatGPT and every other AI. The problem is size. These multi-chip packages have grown massive. We're talking packages stretching past 8,000 square millimeters in some cases. And plastic, under that kind of heat load and at that kind of scale, starts to behave badly. It bends, it shifts. The technical term is warpage. The substrate literally curves slightly under heat, and when it does, the thousands of microscopic connections between chiplets get pulled out of alignment. Signal quality drops, failures creep in, yields get worse. Intel actually gave this problem a name, the Warpage Wall. In January 2026, when they launched the world's first commercial chip using a glass substrate, the Xeon 6 Plus Clearwater Forest server processor, they did it specifically because plastic had hit that wall. Glass was the only way forward. But here's where it gets geopolitical fast. The moment Intel proved glass substrates work in a real shipping product, China, which had already been quietly betting on this for 2 years, suddenly looked a lot less crazy. The US strategy for containing China's chip ambitions has been built around one central idea: control the machines that make advanced chips. Specifically, ASML's extreme ultraviolet lithography systems, the only equipment on Earth that can print transistors at the most advanced scales. Each one costs around $200 million. The US pressured the Netherlands into blocking exports of these machines to China. No machines, no advanced chips, no AI dominance. Simple. Except China didn't try to get the machines. It looked at the chip war and asked a completely different question. What if the real leverage isn't in the transistor? What if it's in what the transistor sits on? That reframe is what the $1 billion in glass is actually about. Why glass, and why it's so hard to make. Glass sounds like a downgrade, right? We think of glass as fragile, drops on the floor and shatters. So why would you build the future of AI chips on something that breaks? Because semiconductor-grade glass is nothing like the glass you picture. It's a completely engineered material, and what it can do compared to plastic substrates is not a small improvement. It's a generational leap. Start with the warpage problem. The reason plastic substrates bend under heat is that plastic and silicon expand at different rates when temperature changes. Engineers measure this as CTE, which stands for coefficient of thermal expansion. Plastic has a CTE that's way off from silicon's, so every heat cycle creates stress between the two materials. Over time, that stress causes the substrate to warp, pulling connections apart. Glass, when engineered correctly, can match silicon's CTE almost exactly, around 3 to 5 parts per million per degree Celsius. Intel's Clearwater Forest chip saw a 40% reduction in signal loss and a 50% improvement in power efficiency for data movement just by making that switch. Those aren't incremental gains. That's a completely different class of performance. Then there's density. Glass can hold electrical connections called vias at pitches below 10 micrometers. A human hair is around 70 micrometers wide, so we're talking about channels for electricity that are roughly 7 times thinner than that, packed at densities plastic physically cannot support. More connections in the same space means more data moving faster between chiplets, which means faster AI, more efficient AI, and cheaper AI to run at scale. Glass is also an excellent insulator at high frequencies. Signals traveling through plastic lose energy to the material itself, but glass keeps that energy in the signal. So not only do you get more connections, Each connection performs better. The flip side is that making glass substrates is genuinely one of the hardest manufacturing problems in the semiconductor industry right now. The key challenge is called through-glass vias, or TGVs. You have to drill millions of microscopic holes through a rigid, brittle sheet of glass, each hole smaller than a human hair, without cracking the glass and without leaving invisible microfractures that only show up later under heat stress. Then you fill each hole with copper that bonds cleanly to the glass wall without peeling apart when temperatures cycle. The tolerances are extraordinary. The glass has to stay flat to within a few micrometers across its entire surface, and any deviation means the chiplets mounted on top can't bond properly. Early attempts at this across the industry produced terrible yields, meaning most substrates came out defective and unusable. You can't build a supply chain on a process that fails more often than it succeeds. That's why, even though glass substrates have been theoretically understood for over a decade, it took until 2026 for Intel to get one into mass production. The TGV drilling equipment itself is also in short supply globally right now. Companies like Applied Materials are racing to fill that gap, which is a whole secondary bottleneck on top of the primary one. Customers who want glass substrate chips are competing not just for the substrate itself, but for access to the machines that make it possible. That scarcity is real, and it's driving urgency across the entire industry. So why is China anywhere close to cracking this? Because it already had the muscle for it, but just pointed at something else: China's play, and what it actually means. Here's what most coverage of this story misses completely. When people say China is investing in glass substrates, they picture engineers starting from scratch in a lab somewhere, reverse engineering Intel's work. That's not what's happening. China has been working with precision glass at industrial scale for years, just not for chips, for screens. BOE Technology is China's largest display manufacturer and one of the biggest in the world. They make the LCD and OLED panels that go into phones, TVs, and monitors, billions of units. To do that at the scale BOE operates, you need to handle enormous sheets of glass with extreme precision, control flatness across large surfaces, and manage high-volume production lines where defects cost real money. You need the kind of process discipline where micrometer-level tolerances are just Tuesday. That's not the same as making chip substrates, but it's much, much closer than starting from zero. The equipment mindset, the engineering culture, the yield management systems, those transfers. BOE has something else going for it: a partnership with Corning, the American glass giant behind everything from smartphone screens to laboratory equipment. BOE signed an agreement with Corning specifically covering glass core packaging substrates. They're not guessing at the material science. They're building with one of the best glass companies on the planet. BOE's pilot production line for glass substrates is already running. As of June 2026, it's fully automated at a designed capacity of 1,000 units per month. Not mass production yet, but a validated and automated process is not nothing. That is genuinely the hardest part to get right. Visionox, another Chinese display company, announced a 5 billion RMB investment, roughly $700 million, specifically for glass substrate development, with supply chain build-out starting in the second half of 2025. PCB maker AKM Meadville has a pilot line. Yuntian Semiconductor, already in Huawei's supply chain and recognized for its glass substrate work, is scaling up too. On the equipment side, Hans Laser is now delivering domestically made TGV laser drilling systems, so China is building the tooling and not just importing it. Industry analysts tracking the South Korean supply chain say China has essentially caught up to South Korea in TGV drilling and etching, the two hardest technical steps in the process. South Korea's Absolix has been the global frontrunner. Closing that gap in the time China did is not what you'd expect from a country starting from scratch. The total capital flowing in, between state semiconductor funds and direct corporate investment, is over $1 billion, with more committed as technical milestones are hit. Xi Jinping has explicitly framed AI as a core national priority through China's next 5-year plan. This isn't a side project. It's a declared strategic objective backed by the full weight of the Chinese state. Now here's the part that should make the West genuinely nervous. The US export control strategy assumes that if you block advanced lithography machines, you block advanced chips. But glass substrates are a packaging technology, not a transistor technology. You don't need ASML's machines to make them. You need precision glass engineering, laser drilling equipment, and process discipline, things China has been quietly building for years inside its display industry. The entire restriction framework that Washington constructed is aimed at one layer of the semiconductor stack. China just bet heavily on a different layer entirely. And if China reaches volume production of glass substrates before the industry's leading suppliers lock in long-term customer agreements, the calculus changes. Chip designers who qualify their packaging supply chains against a Chinese glass substrate supplier don't switch easily. Qualification takes years and costs money no one wants to spend twice. Once those relationships are set, they compound. The supplier learns from every production run. The customer's roadmap gets built around that supplier's specs. You end up with exactly the kind of lock-in that made TSMC impossible to displace in logic manufacturing. China saw that playbook work for Taiwan. It is now running the same play in a different part of the stack, in a segment where its existing industrial base gives it a genuine head start, and at a moment when the rest of the world is just waking up to the fact that this race is even happening. Intel proved glass substrates work. TSMC is aiming for mass production around 2028. Samsung is targeting 2027. South Korea's Substrates could be first to commercial scale before the end of this year. China, with BOE, Visionox, and the whole ecosystem behind them, is moving faster than anyone expected, backed by capital and state coordination that doesn't blink at slow returns. Silicon defined the last 5 decades of computing, but the chip that runs the next generation of AI won't be judged only by the silicon inside it. It'll be judged by the glass underneath it. And right now, China is making a very serious argument that it should own that glass. $1 billion doesn't buy you a chip, it buys you a position. And positions like this, once locked in, don't unlock easily. So, do you think China's aggressive push into glass substrates will let them bypass the chip war restrictions? Drop your thoughts in the comments. And don't forget to hit that like button and subscribe to our channel for more deep dives into the tech and geopolitics shaping our future.